You ever think about how that big bowl of healthy oatmeal you had might not be giving you all the minerals you think it is? It's kind of a nutritional puzzle, isn't it? Like the amount of stuff in the food isn't always what your body actually gets to use.
Yeah, exactly. And that brings us to something really interesting. Anti-nutrients.
Mm.
These are natural compounds, mainly in plant foods, that can, well, interfere with how we absorb nutrients. Think of them as part of the plant's own defense system. Sometimes it makes it a bit harder for us to get the good stuff inside.
Okay, right. Let's dive into this then. Anti-nutrients sounds a bit scary, maybe, but understanding them could actually help us get more from our food, right? It's not about just, avoiding spinach or beans forever. It's more about being smart with preparation. So you can feel better, get more bang for your buck nutritionally without needing a PhD. Consider this your shortcut to being really well informed on this.
Absolutely, that's the goal. For this deep dive, we've sifted through quite a bit of research on these so-called anti-nutrients. They're in lots of common foods, grains, legumes, even some veggies. We'll look at what they are, what they do, and maybe most importantly, how these really old traditional ways of preparing food can make a huge difference. Methods our ancestors used without thinking twice. It's kind of a less is more story, less processing sometimes means your body gets more.
Okay, good. So the mission today is pretty straightforward. We want to give you a clear, practical handle on anti-nutrients. The idea is you walk away feeling, well, more confident making choices that boost nutrient absorption without getting totally lost in the weeds of the science. Sound good? Let's get into it.
Right, so first things first, what are anti-nutrients? Basically, they're compounds in food that interfere with how we absorb or use essential nutrients. Think vitamins, minerals.
And you mentioned they're not just there by accident, they actually do something for the plant itself.
Oh, absolutely. From the plant's point of view, these compounds are super important for survival. They're defenses against being eaten, by insects or animals.
Yeah.
They can fight off pathogens like bacteria or fungi. Some are toxins, some just taste bad. Others make the plant harder to digest. And what's interesting is a plant might make more of them if it's stressed out.
Stressed out? Like how?
Well, if it's damaged or attacked by pests, or even if the soil conditions aren't great, that can trigger more production. And seeds, well, seeds are packed with the future plant, right? So they often have the highest concentration of these defenses.
Ah, okay. So a seed is like a little vault of nutrients with its own security system. Makes total sense. And this gets to a really key point, doesn't it? Just because the label says a food has X amount of iron or zinc.
Doesn't mean your body can actually grab all of it. Exactly. That's the whole concept of bioavailability. How much of a nutrient is actually available for absorption and use? Anti-nutrients are major players in reducing that bioavailability. A lot of dietary advice focuses on nutrient content, which is useful, but it's not the full picture if bioavailability is low.
It's like having money locked in a safe you can't open.
Yeah, that's a great analogy. And it's rarely just one anti-nutrient you're dealing with in a meal. Think about, say, chili with beans. Beans have phytates and maybe lectins. Then maybe you have it with a side of spinach. Hello, oxalates.
Yeah.
And a cup of tea afterwards. Tannins. All these can add up, creating a kind of cumulative effect, hindering different minerals or digestion in general. Understanding the interaction is pretty key.
Okay, so what are the main culprits? The usual suspects we should know about.
Well, there are a few big ones we run into often. There's phytic acid, often called phytate, oxalic acid or oxalates, lectins, that's a big group, tannins, saponins, and goitrogens. Each has different sources, affects different things, and crucially, we often have ways to deal with them through food prep.
Let's start with phytic acid, or phytates. I feel like I hear that one mentioned a lot, especially around grains and legumes. What's the story there?
Right, phytic acid, sometimes called a mineral magnet, and that's not
Hmm.
far off. You find it mostly in the bran and germ of whole grains, the outer layers,
Hmm.
also in legumes, nuts, and seeds. It's interesting, when you refine grains, like making white flour, you remove those outer layers, and the phytate content drops way down. That's one of those nutritional trade-offs.
Okay, so why a mineral magnet? What's the chemistry?
Well, phytate molecules have these negatively charged phosphate groups. Think of them like little sticky arms. And minerals like zinc, iron, magnesium, calcium, manganese, copper, they tend to have positive charges. So opposites attract, right? In your gut, the phytate binds really tightly to these minerals. This forms a complex, a sort of clump that's insoluble, doesn't dissolve well. Because it's insoluble, your body struggles to absorb the mineral from that complex. It just passes through. And the more phosphate groups on the phytate molecule, the stronger the binding effect. The ones called NSP6 and NSP5 are particularly grabby.
Huh. So if I'm eating a lot of whole wheat bread or brown rice, maybe some beans, and I haven't done anything like soaking, I might be getting less zinc or iron than I thought.
That's definitely a possibility, yeah. High phytate diets can significantly lower the bioavailability of these minerals, especially zinc and iron. This is a bigger deal for people who rely heavily on these kinds of unprocessed staples, maybe without getting lots of minerals from other sources. Over time, it can contribute to deficiencies. Scientists actually look at the phytate to mineral ratio in foods to estimate bioavailability. High ratio means lower absorption. It can even get to a point where you might be losing more minerals than you're taking in a negative balance.
Oh, okay. What about our gut bacteria? Can they help us out with phytates?
Good question. They can, actually. Our own digestive system doesn't really make the enzyme needed to break down phytate, which is called
Oh.
phytase. But some bacteria living in our gut, especially in the large intestine, do produce phytase. So these microbes can help degrade the phytate, potentially freeing up some of those bound minerals for us to absorb. How much this happens varies a lot between people, depends on their specific gut microbiome. And phytate itself can even influence which bacteria thrive in the gut. Studies, mostly in animals so far, show it can shift the balance. Sometimes good, maybe sometimes not so good. It's complex.
It really does make you question that simple mantra of whole grains are always better, doesn't it? At least without context.
It absolutely does. Whole grains offer fiber and other nutrients, for sure. But they also bring that phytate load if you don't prepare them traditionally. Our ancestors figured this out, Soaking, sprouting, fermenting. These aren't just quaint customs. They're ways to unlock nutrition by reducing phytates.
Okay, next up, oxalic acid, oxalates. Spinach immediately jumps to mind.
You got it. Leafy greens like spinach, rhubarb, beet greens, they're famous sources. But also beets themselves, tea, cocoa, some nuts have significant amounts. And here's a key thing. Our own bodies make oxalates too, mostly in the liver. Sometimes that internal production actually accounts for most of the oxalate in our system, maybe 50 to 80%, even more than diet sometimes.
Huh, interesting. So how does oxalic acid mess with nutrients?
Its main thing is binding very strongly to calcium. When oxalate and calcium meet in your gut, they form calcium oxalate crystals. These crystals are pretty much insoluble. So the calcium locked up in them isn't absorbed well, it mostly gets passed out. That's how it lowers calcium bioavailability.
And the kidney stone connection, I know that's a big concern for some people.
Right. Calcium oxalate stones are the most common type of kidney stone. Having high levels of oxalate in your urine is a major risk factor. Now, here's the paradox. Eating too little calcium can actually increase your risk.
Wait, how does that work?
Well, if there isn't enough calcium in your gut during a meal to bind with the oxalate you ate, then more of that free oxalate gets absorbed into your bloodstream. Your kidneys then have to filter out that extra oxalate, increasing the concentration in your urine and making stones more likely to form. Studies actually show this lower calcium intake leads to higher oxalate absorption. So it's not just about cutting out oxalate foods. Making sure you get enough calcium, especially with oxalate-rich meals, is actually protective. The oxalate to calcium ratio in the meal matters.
Wow, okay. That's really important context. Are there other effects besides blocking calcium in kidney stones?
Yeah, there seem to be. Research suggests oxalates can promote oxidative stress in cells. They might also activate inflammatory pathways, like something called the NLRP3 inflammasome. And there's some evidence they could disrupt the gut barrier, those tight junctions between intestinal cells contributing to that leaky gut phenomenon.
Hmm. And do gut bacteria play a role here too, like with phytates?
Yes, definitely. There's a specific bacterium, Oxalobacter formigenes, whose main job, basically, is to eat oxalate in the gut. If you don't have much of this particular bug, maybe antibiotics wiped it out, or you just never had much food, you might absorb significantly more oxalate from your food. So another gut microbiome connection. With oxalates, you've got this potential chain. High intake leads to less calcium absorption, more free oxalate absorbed, which could mean kidney stones, or maybe gut irritation and inflammation. Pairing high oxalate foods with calcium sources is a really practical takeaway.
Okay, let's tackle lectins. These seem to generate a lot of buzz and maybe some confusion.
Yeah, lectins are definitely talked about a lot. They're a really large, diverse family of proteins. Their defining feature is that they bind to carbohydrates, specifically sugars, often found on the surface of cells. You find them in lots of plants, but they're particularly concentrated in legumes, like kidney beans, lentils, soy, peanuts, and also grains like wheat. Nightshade vegetables too, potatoes, tomatoes, peppers, eggplant.
And what makes them act like anti-nutrients? What do they do?
Well, a key thing is that many dietary lectins resist being broken down by our digestion, so they can arrive in the gut largely intact. Once there, They can latch onto those carbohydrate structures on the cells lining our intestines. This binding can cause problems. It can disrupt the cell's normal function, potentially damage them, cause inflammation, and interfere with nutrient absorption across that barrier. Some lectins might even be able to pass through the gut wall into the bloodstream and have effects elsewhere in the body.
So they're like little sticky proteins gumming up the works in the gut lining.
That's a pretty good way to think about it. That binding can directly mess with nutrient uptake by affecting the absorptive cells and their microvilli, those tiny folds that increase surface area. Maybe more significantly, some lectins seem to damage the tight junctions, the seals between gut cells. This increases intestinal permeability or leaky gut. When the gut is leaky, things that shouldn't get through, like the lectins themselves, bits of bacteria, food particles can enter the bloodstream. This can really trigger inflammation and immune system activation.
You mentioned something about mast cells and histamine earlier. How do lectins play into that?
Yeah, this is a fascinating angle. Certain lectins, like one from potatoes called STA, seem able to directly trigger mast cells. Mast cells are immune cells, loaded with histamine and other inflammatory chemicals, and they sit right there in the gut lining. These specific lectins can bind to sugar structures, sometimes attached to IgE antibodies, already on the mast cell surface. This binding essentially signals the mast cell to dump its contents to granulate-releasing histamine. This isn't a classic allergy where you make specific IgE to the food. It's more like the lectin is hot-wiring the mast cell directly. People with allergies or high IgE levels might be more prone to this. And interestingly, cooking doesn't always fully deactivate potato lectin, so this could be relevant for folks with things like mast cell activation syndrome, MCAS, histamine intolerance, or just general inflammatory gut issues.
Okay, wow. And the link to autoimmunity, that sounds potentially serious.
It's definitely an area of concern and active research. The leaky gut aspect is key here. When the gut barrier is compromised, more foreign stuff gets into circulation, potentially overloading the immune system. Sometimes the immune system might get confused. It mounts an attack against a foreign particle, like a lectin or something it let in, but that particle happens to look structurally similar to one of our own body tissues. This is called molecular mimicry. The immune system then mistakenly attacks our own tissues too. There's speculation, for instance, about wheat lectin and thyroid autoimmunity. Plus, if lectins get into the bloodstream, it might bind directly to tissues like the pancreas, joints, thyroid, liver, even the brain. This binding could potentially trigger a direct immune attack or cause damage itself. Now, it's crucial to say not all lectins are the same, and some might even have benefits. So it's not about eliminating all lectin foods. It's more about being aware, choosing wisely, and really emphasizing thorough preparation, especially pressure cooking for legumes. That's key for reducing lectins.
Right. Okay, moving on. Tannins. I think of that dry, puckery feeling from strong tea or red wine.
Exactly. That's the classic effect. Tannins are polyphenols found widely in tea, coffee, wine, cocoa, berries, legumes, nuts, cereals, lots of places. They cause that astringency, that slightly bitter taste and drying sensation. The amount and type vary a lot.
And how do they function as anti-nutrients?
Their main trick is binding to proteins and making them precipitate or clump together and fall out of solution. That's what happens with the proteins in your saliva, causing that dry feeling. Inside your digestive tract, they can do the same to dietary proteins, making them harder for your enzymes to break down and absorb. They can also inhibit digestive enzymes, directly the ones that break down carbs, proteins, and fats. And, like phytates, they can also bind to some minerals, especially iron, reducing their absorption.
So maybe having that cup of black tea right with your steak isn't the best idea if you're trying to maximize iron absorption.
That's definitely something to consider, yeah. High tannin intake with a meal can noticeably decrease protein and mineral absorption, particularly iron. But, like these other compounds, tannins aren't purely villains. There's another side.
Ah, okay. The plot thickens.
Right. Tannins themselves aren't absorbed very well higher up in the gut. So a lot of them make it down to the colon, where they meet our gut bacteria. And our gut microbes have enzymes, like tannases, that can break down tannins into smaller compounds. Some of these breakdown products can actually be absorbed and might have beneficial effects, antioxidant, anti-inflammatory activity. Tannins can also influence the gut microbiome composition itself. Low to moderate amounts might even encourage beneficial bugs like Akkermansia. But high concentrations can act like antimicrobials and potentially disrupt the balance or reduce diversity. So again, it seems very dose-dependent. Moderate amounts might be okay, even beneficial via the microbiome, while high amounts act more strongly as anti-nutrients.
Balance seems to be a recurring theme here.
It really is. It's about the dose, the context, the preparation, and your individual biology.
Okay, last couple on our list. Saponins and goitrogens. These sound a bit more specific.
Yeah, it's opponents you find in things like legumes, again, also quinoa, ginseng. They have this sort of soapy characteristic. As anti-nutrients, they can inhibit lipase, the fat-digesting enzyme, potentially reducing fat absorption. Some studies, maybe more in vitro or in animals, suggest they can increase intestinal permeability, that leaky gut thing again. That could be a concern for sensitive individuals. On the flip side, some saponins might bind cholesterol in the gut, which could be seen as a benefit. So another dual-edged sword. Goitrogens are different. They specifically interfere with thyroid function. You find them in cruciferous veggies, broccoli, kale, cabbage derived from compounds called glucosinolates, also in soy, millet, cassava, lima beans. They can work by either blocking the thyroid's uptake of iodine or interfering with the enzyme TPO, which is crucial for making thyroid hormones. But the impact is hugely dependent on iodine status. If you get enough iodine, moderate amounts of these foods are generally fine. The benefits of cruciferous veggies usually outweigh the risks. Cooking, especially boiling, also reduces goitrogenic potential significantly. High raw intake is more of a concern, especially if iodine is low.
Wow. And it's amazing how plants developed all these defenses and then how humans, over millennia, figured out ways around them.
It's truly remarkable. We have this vast cross-cultural history of preparing plant foods in ways that dramatically lessen the impact of these anti-nutrients. And often these methods don't just reduce the negatives, they actually enhance the nutritional value. These aren't just random cooking habits, they are essentially applied biochemistry, passed down through generations.
Okay, let's break down some of these traditional techniques. Soaking is a big one, right? For beans, grains, nuts.
Yes, soaking is fundamental. Just soaking them in water for a period achieves a few things. It helps dissolve and leach out water-soluble anti-nutrients. Some phytates, oxalates, tannins can dissolve into the water. It can also start to activate some enzymes within the food itself that begin breaking down these compounds. We see studies showing phytate reduction in soaked sorghum and kidney beans, oxalate reduction in soaked leafy greens. The really key thing with soaking, though, is you must discard the soak water. That's where the unwanted stuff is gone.
Right, don't cook in the same water you soaked in. Got it. What about sprouting? That seems popular now.
Sprouting, or germination, is incredibly effective. When you make a seed start to grow, it wakes up its own enzyme systems. This includes activating phytase, that enzyme that breaks down phytic acid. So sprouting is great for reducing phytates. It can also reduce lectins and tannins. And beyond reducing anti-nutrients, sprouting often increases the levels of other beneficial nutrients, like certain vitamins, and makes minerals more available. We see data showing big phytate drops in sprouted sorghum and quinoa, for example. Sometimes combining methods is best, like soaking, then sprouting, maybe even fermenting can lead to really dramatic reductions.
Fermentation, another ancient technique. Sourdough bread, kimchi, yogurt. How does that help?
Fermentation is fantastic. You're basically letting beneficial microbes, bacteria, yeasts, go to work on the food. These microbes produce their own enzymes, including phytases to break down phytates and tannases for tannins. Lactic acid fermentation, common in sourdough and fermented veggies, also creates an acidic environment which helps phytate breakdown. Studies show significant phytate reduction in fermented maize, for instance, and tannins can be reduced too. Plus, fermentation often creates new nutrients like B vitamins, vitamin K2, enhances amino acids, and produces other bioactive compounds. It's a real powerhouse.
And finally, just plain old cooking. Heat. How effective is that?
Cooking is definitely important, but its impact really depends on which anti-nutrient you're talking about and the cooking method. For oxalates, boiling is usually best because the soluble oxalates leach into the water. So boil your high oxalate greens and discard the water. Steaming helps, but less so. Baking, not very effective for reducing oxalates. Lectins and other protein-based inhibitors are often heat-sensitive, meaning heat denatures them, changes their shape, and inactivates them. Thorough cooking, especially with moisture like boiling or pressure cooking, is vital. Pressure cooking is really the gold standard for legumes to knock down lectins. Though, remember, potato lectin can be stubborn. Phytates, however, are generally pretty heat stable. Cooking alone often doesn't reduce them much, unless maybe it's very long cooking where some might leach out, or if it's combined with soaking or sprouting first to activate phytase. But soaking then cooking beans shows a good total reduction. Tannins and saponins can be reduced somewhat by heat methods like boiling or steaming, partly through leaching, partly through some breakdown.
It's just amazing how these simple, low-tech methods can have such a significant biochemical impact on the food.
It really is. And the research backs it up quantitatively. Lowering phytate levels dramatically improves zinc and iron absorption. Studies show this connection clearly. Removing soluble oxalates via boiling makes a difference for calcium bioavailability. It just reinforces that bioavailability is king. Reducing the anti-nutrients is how you unlock the potential. And often, combining methods soak, then sprout, then cook gives the best results.
This really drives home that less is more idea. Less anti-nutrient interference means more actual nutrition for your body.
Precisely. That's the core concept. When your diet is high in anti-nutrients that haven't been reduced, your body basically has to work harder, and your actual need for certain nutrients might increase. Like, the official recommended intake for zinc actually varies based on estimated phytate intake in some models. If you eat a lot of high phytate foods without preparation, you might need more zinc than the standard DRI suggests. So managing anti-nutrients means you might meet your needs more easily, maybe with less food overall.
It's shifting from just focusing on intake quantity to focusing on absorption quality.
Exactly. And for people with sensitivities, gut issues, autoimmunity, it's even more critical. For them, lectins, saponins, oxalates aren't just nutrient thieves. They can be direct irritants. They can damage the gut lining, fuel inflammation, disrupt the barrier, provoke the immune system. Reducing these compounds lowers that constant stress on the gut and immune system, freeing up metabolic energy for healing and balance. It's about reducing the overall biological burden.
This also seems to resonate with some principles behind, say, low-fiber diets or ancestral eating patterns, maybe?
There are definitely connections. While simply lowering fiber might cut out some anti-nutrients from grains and legumes, careful selection and preparation of all plant foods remain key. Many ancestral diets naturally incorporated these anti-nutrient reduction techniques as just, well, how food was done. This contrasts sharply with some modern trends promoting lots of raw or minimally processed plants without considering this anti-nutrient aspect. It emphasizes that the quality and preparation of plant foods matter immensely, not just fiber quantity. Ultimately, prioritizing bioavailability by managing anti-nutrients helps us absorb more nutrition more efficiently. It's less metabolically demanding.
Okay, so pulling this all together, what are the most practical, actionable strategies people listening can use? How do we minimize these things without making life impossible?
Right, let's make it practical. First, embrace traditional preparation. Soak your grains, beans, nuts, seeds, discard the water. Consider sprouting them if you can. It adds another layer of benefit. Explore fermentation sourdough, maybe fermenting some beans or grains yourself. For high oxalate veggies like spinach or beet greens, boiling and discarding the water is your best bet. Steaming helps too. Cook lectin-containing foods thoroughly. Pressure cooking is fantastic for legumes like kidney beans or lentils. Be mindful with nightshades too. Manage tannins. Maybe don't drink super strong tea or coffee right with your iron-rich meal. Shorter brewing times can help. Diversify your diet. Don't rely too heavily on just one or two potentially high anti-nutrient foods. Support your gut health in general. A healthy microbiome might handle things better. And use smart pairings. Calcium with oxalate foods, vitamin C with plant-based iron sources.
And how does someone figure out if they're particularly sensitive? Is it just trial and error?
It often involves some personal investigation.
Yeah.
We know certain foods are high sources. Legumes for lectins and phytates, spinach for oxalates, whole grains for phytates, etc. Individual sensitivity varies hugely, though, based on genetics, overall nutrient status, gut health, existing conditions like autoimmunity. If you suspect issues, keeping a careful food symptom journal can be really revealing. For more complex situations, working with a knowledgeable practitioner on an elimination diet, followed by careful reintroduction, can pinpoint specific triggers. But really, just paying close attention to how you feel after eating certain foods is incredibly valuable information. Listen to your body.
It really does circle back to respecting that traditional wisdom, doesn't it? These aren't just old wives' tales, they're practical biochemistry.
They absolutely are. Reclaiming these techniques isn't about going backwards. It's about applying incredibly relevant knowledge to our modern food context. It transforms potentially problematic foods into nourishing ones.
Okay, so I think the main takeaway here is pretty clear. Understanding anti-nutrients and using smart preparation isn't about fear, it's about empowerment. It lets us unlock more nutrition, supporting our health in a fundamental way. That less is more idea really shines through.
And maybe a final thought to leave people with. Consider how much intuitive wisdom about food preparation might have been lost. Our ancestors, through sheer trial and error over millennia, likely understood things about food synergy and preparation that we're only now rediscovering through science. What if optimizing absorption is the real key?
That's a powerful thought. Maybe the challenge for us is to try incorporating even just one of these techniques regularly. Soak your almonds overnight. Try making sourdough. See how you feel. Could that focus on absorption be the missing piece for you? We'd genuinely love to hear your experiences or any questions this brought up. Let us know. Thank you so much for tuning in and joining us for this deep dive today.